Hello everyone and welcome to MABA's third webinar of 2022, a new technology, hydrothermal treatment of biosolids. My name is Terry Goss and I am today's moderator. I'm a member of the MABA Board of Directors and on the Programming Committee. We have three presentations during our webinar today. The presentations are approximately 25 minutes with about 5 minutes of question at each talk. If you have a question for any of our speakers, please use the Q&A feature at the bottom of your screen at any time during the presentations, and I will ask the question during the Q&A portion after each presentation. Now, I'd like to kick things off by welcoming our first two speakers. The first speaker, or the first presentation, is Next Rung Technologies, Hydrothermal Carbonization, and this will be presented by Eric Oden, co-founder of Seagreen, and John Ellersick, president of Next Rung Technologies. Eric is the co-founder of Seagreen. He is a tech entrepreneur with extensive experience in the startup, international growth, IPO, and trade sales for new startup companies. Eric has an MSc in mechanical engineering from the Royal Institute of Technology in Stockholm, Sweden. John is the owner of Next Rung Technology, an engineering and consulting firm that assists clients with development and commercialization of new sustainable technologies. He has broad experience with developing new water, energy, fermentation, chemical, and biotechnology processes. John has a BS in chemical engineering from Northeastern University and an MS in engineering management from Tufts University. Welcome, Eric and John.
Thank you. Hello, I'm Eric, and thanks for the introduction. I'm really looking forward to show you about Seagreen. And with me, I have our US branch, John from Next Rung.
Good morning and good afternoon.
So I'm going to share my screen here. All right. This is Rosa. She's, I think 50% of all the cows in Sweden are named Rosa, and she produces wet waste. And we're a lot of others that produce wet waste. And that's what we all want to convert to something more useful. I usually say update the inventors. In 2014, I ran into two guys that introduced me to hydrothermal carbonization, and they work for the company in the forest industry, and the forest industry in Sweden needed to look in for new solutions for the bio sludge that they produce there. And they talked to me about the problem and the potential of using this hydrothermal carbonization technology. And after that introduction, we actually started Seagreen. And what we've done is taken proven technology from the forest industry that's been used for hundreds of years and turned into a solution that we call OxyPower HTC that turns the wet waste streams into a dry use of hydrochar. So what we in our process can do is reduce the volume. So for every 5 kilos or 5 tons of waste, we turn it into 1 ton or 1/5 or 20% of the original volume of hydrochar. That can be used for several different useful applications. I'm going to show you the first one here very soon. So this is our first full-scale plant. And when we started 2014, we developed the technology at the Royal Institute of Technology at the lab we had there, and did hundreds of trials for different kinds of sludges, and showed that this works on all kinds of biosolids, digested, undigested, and all kinds of different wet waste streams. We built a pilot plant with a capacity of 1 ton a day. And then we found out that Stora Enso were interested to help us build a full-scale plant. And this is the world's first OxyPower HTC plant that converts about 20,000 tons of wet biosludge into hydrochar. And here's a small film showing it in operation.
I'm here at Stora Enso's mill in Heinola, Finland. Sigrid worked together with Stora Enso to build the world's first OxyPower HTC plant using our unique technology to convert wet sludge into solid biofuel. The plant is now operational, and each year it will turn 18,000 tons of sludge into biofuel. The impact of sludge handling is not so well known, but it is a major climate and environmental problem. Sludge from the treatment of wastewater from industries, households, and food production causes greenhouse gas emissions, can spread dangerous substances in the environment, and can pose health risks. With our new technology, we can lift sludge handling into the modern circular bioeconomy and harvest useful resources from what have been, until now, seen as waste. In this plant, the sludge is turned into a carbonated biofuel using oxygen from the air to power the process. Here at Stora Enso's mill, the biofuel is incinerated in the boiler, which means they need less external fuel. The boiler produces energy for the mill and for heating the town of Heinola. The biofuel is safer and easier to handle than sludge, with a volume of less than 20% of the sludge. Here in Heinola, the water removed from the sludge is used to increase the mill's biogas production and to help reduce the need of chemicals for the biological water treatment. Seagreen's sludge handling technology effectively stops greenhouse gas emissions from sludge storage. The biofuel produced can replace fossil fuels. In future plants, it will be possible to separate nitrogen from the process and replace fossil fuel-based fertilizers. This first commercial OxyPower HTC plant is just the beginning. Here, sludge is no longer a waste problem and a climate threat, but the source of useful bio-based products. This is the solution to the global sludge challenge.
Right. So our approach when it comes to designing plants is both to try to make them beautiful and also to make one that is like the T4, one size fits all. So we've created a plant with a plant design with a capacity of 25,000 tons of wet sludge per year, with the capacity to handle and then 5,000 tons of dry solids. The technology of such, I will come into how it works a little bit. It doesn't require any external heat. And it's built up from prefabricated modules. I will also show how they are built up together. And all in all, it is a very small footprint of a refinery that can handle all this sludge and turn it into something useful. So typically, I mean, you can handle all the wet waste from a city of 200,000 to 300,000 people. And it's fully automated. The plant in Finland will run from Stockholm without any problem, without anybody there for the actual operations. So the basic principle is that we feed in the biosolids into the process and heat it up, and it comes into the HTC reactor. I will go through it a little bit more in the film, more animated. In the reactor, we get two streams out, a slurry rich stream that we dewater and it turns into the hydrochar, and a stream that doesn't have virtually any particles, and that we oxidize with oxygen from the air to create the heat we need to power the process. Most of the nitrogen will end up in the water, and we have the possibility to extract that as in the form of ammonia as well. A nice effect of wet oxidation is that the ammonia that comes in many forms are turned into, and the nitrogen that comes in many forms are turned into ammonia. which is quite handy. So what happens when you heat up the waste? Very, very quickly, at around 200 degrees, it turns into this carbonated particles that are hydrophobic. So the actual carbonization goes very, very quick. But the particles are very small, and to be able to dewater them effectively, we need to have a retention time. Typically, we use about 1 hour to have an efficient dewatering. And what's quite interesting and fascinating, if you worked a lot with biosolids, that is very, very difficult to dewater, is that the stream with the particle-rich stream separate very, very easily and nicely if you take it out from the reactor, and you can see that in the film here. The water that we take out, the particle lean water, I have it here as well, look like coffee, and about 30% of the organic material will end up dissolved here. So it's a lot of COD, BOD in this one. And of course, that's a good energy carrier. So we thought, how could we make use of that and clean it at the same time? And also, how could we find a way to power the whole process? Because I mean, we constantly need to heat up the incoming stream of biosolids or waste. And we came up with the idea to use wet oxidation. And when we add oxygen at 200 degrees, you get the wet incineration and you remove the COD. And the more oxygen you add, the more you move it. So you can go, actually, if you have used catalytic wet oxidation, then you can remove all the COD. So you can see it's a huge difference. So here we have a gas pedal to use to clean the return water, and also to produce the amount of heat needed, and also extra heat if that is of interest. And you at the same time have the nice effect that the nitrogen is converted to ammonia. So our plants are modular and designed to be built in large scale. So here you can see the modules, how easily it is to transport them to site, put them together, and build a plant. In you have water and sludge and electricity, and out you get the hydrochar and the return water. In this process, we feed in the sludge and heat it up with steam in steps, so there are no indirect heat exchangers. And so with higher and higher pressure, at the end, it's about 200 degrees, and it goes over to the reactor where we have a guaranteed retention time. And in the bottom of the reactor, we have a particle-rich stream, and in the top, we get the particle lean. And the particle lean, we get into a separate reactor where we add the oxygen, and then you get this wet oxidation, you increase the heat. And then we have very hot water that we can use to produce steam by reducing the pressure. And then we get the steam for the incoming sludge and to heat it up. And that's by reducing the pressure in a step called flashing. We produce steam with different pressure and different temperatures to heat up the incoming. And the same we do with the slurry fraction. And that slurry fraction, after we recover the heat, we use it, the water to produce biocoal, and the other one, the particle lean one, is sent back for water treatment, for example, to a wastewater treatment plant. And as a final step, we dewater the slurry, and we use a filter press for that. And out you get the dewater hydrochar. So this is a very short version of how our process works and how the plants are designed. So by having this modular approach, we could set up an assembly line and easily produce these different container-sized modules that are uniquely configured. and thus being very efficient in producing several of these. And we could set up first an assembly line in Europe and then built one in North America, which is our plan. All right, so some of the properties of Hydrochar, I guess all of us are going to talk about that, but it's a very interesting product. It's very peat-like if you haven't seen one or seen the Hydrochar. And of course, due to the temperature of the process, it's sterile, and the smell is very similar and independent on what the feedstock you use, which is quite nice. And of course, depending on how much carbon you have in organic matter you have in the incoming feedstock, you will have more or less energy in the Hydrochar. It's quite inert, and it's easy to turn to pelletize. And when you pelletize it, it's very, very stable. I have some pellets here, and they were pelletized for several years ago, and you can put them in water and nothing happens, since they are hydrophobic. Just to show you, I mean, we've done trials on all kinds of different feedstocks, here, just to show, and I mean, depending what you put in, you will get something similar out in the other end. So the more carbon you have in the feedstock, the more carbon you will have in the Hydrochar, and that will, of course, be the same for all kinds of components. And so here just an example: manure, which is quite carbon rich, or the pot biosludge. If so, I mean, and digested sewage sludge works fine, but you will have a Hydrochar with a lot less carbon than undigested, for example. And that will, of course, impact the different possible uses of the Hydrochar. So where does different components end up? Most of the metals will end up in the Hydrochar, especially the heavy metals. So we have a high recovery of those in there, if you're interested in that. And of course, in the phosphorus, which I think is very simple, it ends up in the Hydrochar. Today we are not only working with the first full-scale plant in Finland, we are building several more in Europe. So in Stockholm, in the Stockholm region, we're building what we call the world's first biosolids-free wastewater treatment plant, where we will integrate our OxyPower HTC plant with their treatment works. So you will, the in-feed will be sewage, and out we will only get Hydrochar and clean water. And we are together with Ragn-Sells, which is a waste handler, the biggest in Sweden, building a plant at one of their waste recycling facilities. We're actually building one more with another waste handler in central Sweden that are focused on having cleaner streams. So their focus are not biosolids, it's forest residue and biosludge. And their focus is to make a peat, biopeat. So that's an additional one. Remondis, which is one of the largest, or if not the largest private waste handling company with 30,000 employees. They have operations in Netherlands through the company Rime, which they own to 100%. With them, we have started a project to build a plant for industrial sludges, which I think is very, very interesting. We have a very, very interesting pipeline, and I cannot go into the name of these companies, but it's all signed MOUs with the intention to build plants if everything follows plans and they get the permits and the pre-studies are resulting the way we anticipate. So we have a very, very interesting pipeline here of plants to build in Europe. And now we want to take this technology together with Nextron to the US. So John, leave over the word to you.
So I'm John Elisick with Nextron Technology. We have collaborated with Seagreen for over 2 years now Looking at the opportunities in the United States, which are strong and many, and how this technology fits in the U.S. market. There's plenty of differences between the U.S. market and the EU, and also some things that are similar. And I'll just highlight a few other things we think about here, like the reduction in sludge volumes by themselves are very meaningful, especially in an environment where it's difficult to truck or transport solids. I think everybody here is familiar with challenges around landfill costs coming up. Landfills even closing to municipal biosolids, changing regulations and tolerance for land application, issues around the emergence of PFAS throughout the country. And then here, I would say in the United States, the sustainability is just becoming to the forefront of municipalities, whereas I think in Europe it's been there strongly for a while, and people are realizing that that how you manage your biosolids is a large part of achieving your low carbon or net zero solutions. So to go to the next slide, Eric, we've been actively conducting outreach in the U.S. for the last year and a half, and collaborating with all the different parties in the ecosystem, whether it's municipalities, consulting companies, engineering companies, solids aggregators. We've got a team of folks who are located at Greentown Labs, which is America's largest clean tech incubator here in Somerville, Mass, and also in Houston, Texas. And we're working to further work with U.S. sources, including setting up a lab for testing of various biosolid sources in the United States. And we're active and involved in the biosolids organizations, including MABA, CASA, West Coast and East Coast. We will be at the NUIA conference as well as the WEF conference over the next week or two. So we look forward to seeing even more of you in person. And with that, and on time for Terry, I think it's a good time for questions.
All right, thanks, John. Thanks, Eric. When looking through a good presentation, I had a question on the filtrate from the dewatering after the wet oxidation. Is that facility, was that going to an anaerobic digester for further treatment, or what was the?
This filtrate, it's going to be different from case by case. But for example, in Heinola, then it goes to a digester and it increases their biogas production. What happens is that the organics that's left is highly biodegradable, so it's quite easy to convert into biogas. Okay.
The facilities that you're doing that are going to be municipal with sewage sludge, what's the plan for those? Is that also anaerobic digestion?
Yes.
Okay.
Where that is, where they have that so it's whenever there is a digestion facility, that's going to be where we send back the return water. If that's not the case, of course, then it's going to be sent back to the beginning of the inflow
to the headwaters.
Yeah.
Okay. And have you done treatability tests on that to see how well that would work in like a a conventional activated sludge process?
We've done all kinds of trials for different wastewater treatment plants and different technologies to see if it has some impact on the different steps in the wastewater treatment plants.
Okay.
Yeah.
Okay. All right. There was a question that come up that was asking about the fate of PFAS and PFAS destruction in the process.
Yes, and that's something we're taking very seriously, because we hear that a lot, especially in North America, but we see this issue also coming up in Europe. The concentrations we found here are very, very low. We've tried to do a few trials and doing an investigation together with the Swedish Environmental Institute that has the possibility to measure these. And we see indications, but we don't have final answers yet. I think we need to continue this.
And Terry, our strategy, I think in the States as well, will be, we're looking to receive individual samples of folks' municipal sludges that are representative, in this case, do in fact some PFAS testing before and after of the liquid and solid streams. as part of setting up labs here. So
Okay.
I think there's a case-by-case element to that, but it's fully on our radar screen.
Okay. All right, great. Another question, what are the carbon sequestration properties of the char?
The carbon what?
Sequestration.
So I don't.
So
I don't think.
this stability of carbon as hydrochar as opposed to as land applied biosolids. So I think in general, there's a longer release time of carbon that I believe Eric can correct me, but that's over the course of something like 4 to 7 years, as opposed to land applied biosolids, which I believe have sort of an annual cycle of release of the carbon, as well as potentially in the form of methane from land applied biosolids. So it's preferential in that regard.
All the studies we've seen, and we haven't done trials. We haven't done agriculture trials for a year or 2 years, but it's not a long enough time. But we know there's all kinds of research in the field to see how long does it stay, the carbon stay in the ground, and it's a lot longer, of course, than the biosolids itself, but it's shorter than pyrolysis biocoal. So it's somewhere in between.
Okay. And Samantha McBride, I just asked about the contact about samples. So with New York DEP.
Yeah, if you go to the last page of the slides, and we'll make sure this is available. If you reach out to us, Samantha, there you go. Suzanne, who is also on this conference, myself are the sort of the US contacts, and we can set up receipt of any sample materials.
Right. So with one last question, and then we'll move on to the next speaker. But with the wet oxidation process and getting energy out, is that how that energy balance, does that work where there's excess heat that still needs to be wasted, or is there, or how does that work?
I mean, we add the amount of oxygen from the air that's needed to power the process.
Okay.
And initially we need to kick it to start it up. So we need some kind of heater. We use an electrical heater, but one could use other kinds of heater as well to heat up the system to around 200 degrees. And then it works by itself.
And what pressure is that tank?
The pressure, I mean, we're typically running at around 20 bars in the HTC process. For the wet oxidation, I think we add oxygen at a little bit more than 30 bars.
And so I'd say, Terry, there's some opportunity to tune it per application. If for some reason you had a use for that heat, you might do further wet air oxidation than in the case that you're simply trying to have a closed heat loop.
Okay.
Yeah, and we have customers we talked about that have biogas plants nearby that needs the heat to keep them hot enough to have a good speed in the biogas production, and then they need heat for that.
Okay. All right. Well, great. Well, Eric, John, thank you for the presentation.
Thanks a lot.
Thank you for having us.
Yeah, thanks.
All right. So next we'll go on to Jeremy Taylor from SOMAC Circular Solutions. And he's going to present hydrothermal carbonization, an update on HTC at the Borough of Phoenixville wastewater treatment plant, and biocoal product development. Jeremy graduated with a BS in chemical engineering and MS in sustainable engineering from Oklahoma State University and Villanova University, respectively. Jeremy connected with SOMAX during his master's studies in 2018 and has focused on developing and deploying commercial scale hydrothermal carbonization facilities ever since. Holding the title of Chief Sustainability Officer with SOMAX since graduation in May 2019, Jeremy has helped develop the first commercial scale HTC implementation in the United States at the Borough of Phoenixville wastewater treatment plant. He continues to develop HTC product markets and build the case for HTC and other high organic waste industries. Welcome, Jeremy.
Awesome. Thank you, Terry, for the intro and moderating the session. And thank you to the Mid-Atlantic Biosolids Association for having me to speak today. Eric, John, great presentation. I really look forward to having you guys in the US market and push HTC forward. So agenda today, a little intro to SOMAX. I'm going to go a little bit deeper into the science of HTC and hopefully educate you all a bit more on what takes place inside of the reactor and during the HTC process. And I'll give you some updates about the Borough of Phoenixville HTC project, as well as discuss product development pathways that we're pursuing. So in 2015, Dan Spracklin, CEO of SOMAX, partnered with Villanova School of Sustainable Engineering to identify ways to handle his septage. So SOMAX is a spinoff out of a septic company with research backing by Villanova. Since then, we've sponsored 8 master's theses, myself being one of them, and we've established hydrothermal carbonization as our cornerstone technology. In 2018, our technology partners developed their 3rd generation pilot unit, which is the type of reactor that's being installed at the Borough of Phoenixville. In 2019, we were awarded the design build contract for the first HTC plant in the United States, with hopes of commissioning in Q3 of this year. In 2021, we had 2 big wins. We were one of 2 grand prize winners for the Water Resource Recovery Prize put on by the US Department of Energy. The other grand prize winner is on this call, is Genefuel. Congrats to you guys. The US Department of Energy was seeking scalable, repeatable solutions for small to mid-sized wastewater treatment plants across the US, seeking to recover 50% more resources than currently being recovered. Also in 2021, we were winner of a low carbon heat challenge from one of the world's largest spirits companies. So we've been doing a lot of work with spent distillers grains, and that's been a really interesting industry to get into. So SOMAX approaches our customers with our resource recovery platform, with HTC as the cornerstone technology and a number of other technologies provided by other technology providers to kind of close the loop on water recirculation for carbon neutral energy generation and returning nutrients to our soils. The platform acts as in turns a one-way transaction into a cyclical flow of materials and revenues. So again, HTC is our cornerstone technology, and we partner with a number of different technology providers to provide these solutions to our customers. Before getting into HTC, I kind of want to talk about the current organic waste solutions and compare some core metrics of HTC versus the status quo. So the 2 things I mainly want to look at are carbon efficiency and process duration. Carbon efficiency is a metric that measures the amount of carbon in the final product as compared to the carbon in the original feedstock. Landfilling organic waste essentially has a 0% carbon efficiency, with the exception to landfills that actually have landfill gas capturing and reuse. Composting, while good, has a low carbon efficiency of about 10% and a long process duration, requiring a large amount of land to handle these large compost operations. Anaerobic digestion, which is the status quo in the industry, has a carbon efficiency of about 15%, or 50%, my apologies, and takes 15 to 40 days to complete. Where HTC has a carbon efficiency of up to 90% and a process duration as little as 3 minutes to 4 hours. So we're able to process material in a much smaller footprint than these other technologies, and do so with a higher carbon efficiency. And this carbon efficiency, it can translate to a means of energy recovery and utilization. So in one presentation last summer, a company said that out of 1 ton of source separated organics, they can get about 4 MMBTUs of biogas from anaerobic digestion. That same 1 ton of source separated organics through HTC can produce 6.5 to 7 MMBTUs of energy in the form of hydrochar. That's a 60 to 75% increase in energy recovery and utilization. So what is hydrothermal carbonization? This slide feels a little redundant with the presentation that was just given. So I'll talk about our technology a little bit and then get into the reaction mechanisms that drive the carbonization process. So in the 2 pictures below, we have the Generation 2 reactor and the Gen 3 reactor that went live in 2018. With the Gen 3 design, we were able to containerize the solutions. So we have a container for our heat exchanger, a container for our reactor, and ancillary equipment outside of the systems. And we get an idea of what this footprint looks like later on, looking at Phoenixville. So this containerized solution allows us to be quickly deployable, highly modular, and easily scalable. We've decoupled the heating phase from the reaction phase in this system, and it allows us to scale down quite nice. At this lower end of our system, we can do 2,000 tons per year. While it doesn't scale economically, it is doable. At Phoenixville, we're doing about 15,000 tons per year at a roughly 15% solids. I would like to bump that up to 20% solids as we get it commissioned up and running, but currently targeting 15% solids. So let's get into some science. Here are some reaction mechanisms around carbon that take place in the hydrothermal carbonization reaction process. So the first step is hydrolysis. I'm sure all of you are aware of what hydrolysis is. The Canby process, LizTech, both of those utilize hydrolysis. It takes a subcritical water to cleave larger molecules, making them more bioavailable or more chemically available for later reactions. Another reaction mechanism is decarboxylation. This creates CO2 gas. So the primary emission associated with the H2C process is CO2. It makes up about 95% of the gaseous emissions of H2C. Another step is dehydration. This actually creates water. So it attacks hydroxyl groups and makes a more carbon-dense structure with fixed carbon and creates water. Additionally, the condensation reaction creates water as well. You see a condensation or repolymerization of these compounds, making more stable carbon compounds while creating water. So the common theme here is water is used to cleave molecules. It's also a product of some of these reactions, hence the name hydro and thermal. All of these reactions make a more carbon-dense material as well, and that encapsulates the final name, carbonization. Getting to the reaction mechanisms around nitrogen, these are a bit more hairy than the ones around carbon, but the core reaction mechanisms are amide formation and deamination, and those two basically mirror each other. Amide formation is when an amine forms with a carbon compound. The amide formation can be a dehydration mechanism where an ammonia or molecule or an amine compound attaches in place of an OH group. So similar to the dehydration carbon mechanism, it can be done with an amine forming an amide and creating water in that process. Deaminization is essentially the opposite of that reaction. And with this, you see about 50%, give or take, of the nitrogen in the original feedstock make its way to the liquid solution. The last reaction here is Maillard reactions. It's a whole suite of reactions that make heterocyclic nitrogen-containing compounds that may become part of the solid matrix. Going a little bit deeper in the science, one of the products of Maillard reactions is hydroxymethylfurfural. This is hypothesized to be one of the core compounds to make secondary char. So primary char is the solid matrix that is being transformed into a more carbon-dense material without materials going into solution. Secondary char is those compounds that have been released into the solution, recondensating and polymerizing into a secondary char. So primary char is just the changing of the solid matrix. The secondary char is the recondensation of those released molecules to solution back to the solid matrix. And that's what really sets H2C apart from some of the lower end thermal processing. One thing to mention too is Maillard reactions is something that you all have done, whether you know it or not. It's the reaction that takes place whenever you're cooking a steak and it browns and you get that good caramely burnt roasted flavor mixed into your steak, or if you're roasting grains before brewing or any of those, that is a Maillard reaction. So pointing out those reactions and speaking to them is quite easy, but whenever you see the compound soup that is associated with food waste or with sewage sludge, the exact compounds that get generated are pretty tough to track. Getting into reaction trends, I think Eric did a good job of pointing out that the biosolids digestate is not necessarily the best feedstock for fuel generation. What we're looking at here is proximate analysis and higher heating values of 3 different feedstocks at 2 different reaction temperatures. The blue, red, and black represent proximate analysis results of volatile matter, fixed carbon, and ash. The green dots are the higher heating values associated with it. So the trends that take place are as the temperature increases of H2C reaction, you see higher heating values in that hydrochar. And that's due to more reaction severity driving these reactions. So with approximate analysis trends, you see a decrease in volatile matter, an increase in fixed carbon, and an increase in ash content. And Eric again had mentioned that the metals primarily stay in the solid matrix, and that's why you see the ash content increasing. Getting into hydrochar and comparing it to some other coals or fossil coal. So hydrochar is also commonly referred to as biocoal or biogenic coal. Depending on the feedstock that's used for HTC, it can be compared to different fossil coals. So the raw sewage hydrochar is on that high end of lignite fossil coal, which we can produce in about 1 hour, as opposed to 60 million years that it takes to form lignite coal. Hydrochar made from mixed food falls in between that bituminous and subbituminous range, with lower ash contents of about 2 to 5%. The holy grail of hydrochar that we've made has been made from spent grain, which has a heating value between 14 and 16,000 BTUs per pound, which is higher than even that of anthracite coal. The ash content is surprisingly low at only 0.5 to 1.5%. And it has, it's able to be made from a biogenic source as opposed to anthracite coal, which has taken 350 million years to make. So the hydrochar heating values range anywhere from 9,000 BTUs per pound up to 16,000. And from a carbon accounting standpoint, has a net zero carbon emission factor if used as a solid fuel. This is similar to renewable natural gas. We're making a biogenic coal to replace fossil coals. So I railed on anaerobic digestion a little bit earlier, but as Eric mentioned, sending the process water from HTC back to anaerobic digestion can boost the biogas production. So this is a study looking at the organic fraction of municipal solid waste and sending process water back through anaerobic digestion, which produced 30% more biogas. And at the bottom process flow diagram, that's sending the entire stream through HTC and then into anaerobic digestion. And they saw results of producing up to 300% more biogas production, while also lowering the hydraulic retention time necessary for that anaerobic digestion process to function. So there are some really nice synergies between these two technologies. So it's not just the process water that helps facilitate the biogas production. There are some volatile surface functionalities that are bioavailable. But in the Pages Diaz study, they point out an additional means of how hydrochar facilitates its biogas production. And to be honest, this is beyond my understanding of anaerobic digestion, but the hydrochar assists in biogas production through improving the hydrogenotrophic methanogenesis by converting hydrogen ions, electrons, and CO2 to methane due to direct interspecies electron transfer. And that's just beyond me, but I'm happy to give you all the paper if you'd like to look into that more. So a question that was asked previously is what happens with PFAS? It's still not fully known where the PFAS goes to in the liquid stream, or what they get converted to if they do at all. This study was done out of Germany in 2016, taking sewage sludge, converting it at 210 Celsius for 4 hours. The sum of the PFAS in the sewage sludge was 104 micrograms per kilogram. And the sum of all PFAS in the hydrochar was 32 micrograms per kilogram after HTC. So it's a 2/3 reduction in total PFAS. And that number is important because in Germany, it meets the threshold for land application. So the sewage sludge by itself did not meet the land application criteria, where after HTC it did. We also saw a complete removal of PFOA. So I want to put it out there, if there are PFAS testing companies that are comfortable testing solid matrices, get at me, let's do some PFAS testing. We have samples lined up and are looking to go in depth on this and track PFAS throughout the HTC process. So that's it for the science on this. And we can start talking about the Phoenixville facility. So the Borough of Phoenixville branded the HTC facility as the PXV NEO, the Phoenixville New Energy Optimization Hydrothermal Carbonization Facility. They're really leaning into this. They're going to get a big mural painted on the facility. It's awesome. If you want to track the construction of this, check out the website at pxvneo.com. So the borough of Phoenixville is a small town. There's a population of about 17,000, but they're very progressive. They're the first municipality in Pennsylvania to pledge to 100% clean, renewable energy by 2035. They did an energy audit and found that their wastewater treatment plant was the largest energy consumer, and they wanted to see what they can do to take it offline. This is when we met with Phoenixville and told them about HTC and its capabilities of being an energy producer for their municipality. After the feasibility study, we found that we could produce more energy than their wastewater treatment plant consumes. And they were sold on implementing HTC and eventually gasification of the hydrochar. So our current project timeline with Phoenixville, we started in 2019 with the engineering design. Currently, we are under construction and we're waiting on one final piece of equipment to arrive. That's our inlet pump. Once that is in place, we'll be laying pipe and in construction in earnest. In Q3, we're hoping to commission the HTC facility. With current supply chain issues, I'm sure there's going to be some oddball thing that keeps us from doing that. And my pessimistic view is we'll be doing it in Q4. For those engineers that are on the call today, if you have went through the past 2 years without any delays on your projects, congrats, because COVID and supply chain issues have been a headache. In 2023, we're going to increase feedstock procurement, so open up the facility to bring in hauled waste, and we're going to be proving and permitting the beneficial use cases of the hydrochar. With that, we will be applying for a Pennsylvania general permit or an individual permit at the treatment plant. And around 2024-25, we'll look to implement phase 2, which combines food waste feedstock into the HTC process and includes gasification and cogen for carbon neutral electricity generation. Here's the wastewater treatment plant process flow diagram. I'm sure you all have seen many of these, and there's nothing too special about it, but I want to point out where we tack on to at wastewater treatment plants. Right at the point of dewatering and prepping your solids is where HTC gets tacked on. So in this case, we will be taking over their centrifuge and using that to feed the feedstock into our system and using the Biosolids storage greenhouse and putting our HTC equipment there. We'll be doing away with land application of their sludge. So again, we have that integration point at the treatment plant, and then we get into our HTC process. So we take that the centrifuge sludge that's about 15% solids, get it into a live bottom storage hopper, which feeds the piston pump. And the piston pump is a workhorse for our process. It moves the sludge through the entire process to the depressurizing pump. The cold substrate enters a double pipe heat exchanger, which has a water loop in it. And that gets the material up to about 160 Celsius. From there, it goes to our specialized jacketed heaters, where they're jacketed with a thermal oil. That thermal oil heater can be electric. The one in Phoenixville is natural gas fired, and it consumes about 1.33 MMBTUs per hour of natural gas when processing 15,000 tons per year. When the heated substrate leaves the heaters, we're at about 205 Celsius going into the reactor. We lose a few degrees throughout the reactor, and then that product slurry goes through the double pipe heat exchanger, heating the cold substrate. From there, it passes through a depressurization pump and into a buffer tank where it is held to be dewatered. You'll note that there is some odor control on this. This was to really work through the air permitting guidelines from DEP, and we were able to not have a defined air permit on this process initially when applying these activated carbon drum scrubbers. The emissions associated with HTC are not nearly as pungent or smelly as the raw sludge that will be in the live bottom storage hopper. But it's an unknown to PADEP, and they wanted there to be odor control. Out of the buffer tank, we go into our dewatering press, where we get a dewatered hydrochar that is 50 to 60% total solids, and the process water goes to the headworks to be treated. So this is our dewatering press. We use what's called a Booker press. This thing is like the Bugatti of dewatering presses, and that seems silly, but this thing is really, really nice. So the entire body of this thing slowly rotates, and it compresses like an accordion. So it fills up with water or hydrochar slurry. It compresses. The filtrate goes through those drainage cores, which is the socks that you can see in the picture. And as it compresses, it opens back up, and it goes through a fill cycle to where it opens and closes a few times to get filled with solids. And then it goes through a dewatering phase where it really compresses those solids and drives the filtrate, the process water, out of that. What's really unique about dewatering hydrochars is able to be done polymer free. And due to the hydrophilic nature of the hydrochar, you're able to get very high total solids. So we're seeing 50 to 60% total solids hydrochar coming out of this. With acid addition from our pilot unit, we saw upwards of 70% total solids, just unprecedented dewatering capabilities with HTC. And some of the specs on this, we're seeing greater than 99% solids capture and a filtrate with less than 100 milligrams per liter of suspended solids. So something that should be noted is HTC plus drying of the material, taking it from that dewatered state to dry, uses up to 60% less energy than just drying of biosolids alone with conventional dryers. So if you're doing gasification or pyrolysis, this unit will drastically decrease your drying needs, with the potential to remove your dryer altogether, with some of these gasification technologies taking in solids that are about 60-65% total solids. So this is what our equipment layout looks like in Phoenixville. On the right side here, we're looking at about 60 feet wide, and up to this garage door, which I pointed out previously, is about 115 feet. We just talked through the process flow diagram, but I will do it one more time real quick so you can see what these components are. This is the live bottom hopper. It feeds the piston pump, which goes into this dark orange line, feeding our heat exchanger. The heat exchanger feeds the heaters. Heaters are powered by or heated by a thermal oil natural gas fired heater here. From the heaters, it goes into the reactor to heat exchanger to depressurization pump to buffer tank, and then dewatering from there. So here's some construction pictures. This is what the greenhouse looked like before we started. You can see it was mainly just used for biosolids storage. A logistics company would come and pick it up every couple months and go and land apply the material. To hold the weight of the equipment, we needed reinforced concrete, and we wanted to put in some integrated piping as well for plumbing and drainage. So we did one side at a time. And if you can see in this picture, we still have biosolids being dropped on this far end here. So the production of biosolids and the wastewater treatment process was not interrupted during this construction. Here's what it looked like prior to setting equipment. This will probably be the cleanest the floor has ever been inside the greenhouse. Here is a picture of the live bottom hopper. This thing is a tank. It holds about 1 day's capacity, which is around 10 to 11,000 gallons of sludge. It's not fully constructed here. There's no catwalk up top or guardrails. It's just getting it placed. Here's a photo of loading the heat exchanger or reactor into the greenhouse. If we were to do this again from a clean plot, we would put the equipment in the greenhouse before putting or into the building before putting the roof on. It would make construction a bit quicker and less stressful. Here is a picture of the heat exchanger being placed and the guardrails up on the hopper. Here you can see our heater skid is in place as well. And here's a picture of the reactor getting set inside the greenhouse. So we'll have our buffer tank here, and then the Bucher press sits about where those drainage cores are, or the drain is. Oh, I'm coming up on time. So a couple more slides left. Here's some hydrochar utilization potential, and I'll highlight the use cases that we're pursuing at Phoenixville. So in this blue bubble, we will be pursuing using hydrochar as a solid fuel, getting it permitted as a solid fuel in the state of Pennsylvania. And at phase 2, we will be looking to gasify this material as well. Biogas is not necessarily going to be used at Phoenixville, but as Eric had pointed out previously, it can be integrated with HTC. We'll not be touching the renewable energy storage potential uses with the sewage sludge hydrochar. This takes much cleaner feedstocks to even consider making those materials. In agriculture, one of the cases we're going to try to get permitted is as a land applied Class A biosolid. It's not what we want to be doing, but as steps to progressing to these beneficial uses, it's going to have to be applied for. Also, we're going to be looking at extracting fertilizers from the processed water. We're working with the chemical engineering department at Villanova this coming school year to do some studies there. We have a PhD research study underway currently looking at water and gas purification from hydrochar. This looks at not only the hydrochar, but pyrolyzed hydrochar and then activated hydrochar for heavy metal absorption and for the potential for stormwater runoff. In the sustainable building materials sector, we are looking at using the concrete and asphalt additive. So we have a number of partners wanting to test this material as a fine aggregate replacement, so replacing sand and concrete. And once we're commissioned, we'll have volumes that are worth sharing and the ability to test some of these use cases at larger scales. Initial results of using it as a sand replacement in concrete showed that at lower concentrations, up to about 10%, the concrete mortar still maintains a 4,000 PSI compressive strength. And at higher concentrations, up to 30%, the compressive strength is impacted pretty substantially, but still has the opportunity for non-load bearing applications such as sidewalks and precast materials. Lastly, this falls in the same vein as activated carbon or as the water and gas purification. We've done some activated carbon testing at Villanova. And what we saw is that low concentrations of methylene blue dye, it was comparable to commercially activated carbon. And at higher concentrations, it was about half as effective. So not something that's like a really something to write home about, but it is a potential use of using this hydrochar as is for water treatment and stormwater remediation. So our approach to permitting in Pennsylvania, we're currently permitted as a captive municipal waste processing facility under a permit by rule. But under a permit by rule, the hydrochar is still considered a waste and must be stored on site until approved for whatever beneficial use we're going to be using it for. There is an exception though. We're able to send it out for beneficial use testing, and that's when we'll really tap into our partner market and get some of these potential uses, potential use testing underway. So like I said, we need to get it approved for landfill, land application. It meets the solid fuel requirement easily, which is 5,000 BTUs per pound. And we'll start the beneficial use testing at pilot scale with our partners. The hydrochar can be de-wasted for beneficial use with an individual or general permit. And that allows us to sell this into the market and treat it as a actual material and commodity and not as a waste material. So lastly, some takeaways for you all. HTC is being commercialized in the United States, not only by Somax, but by our friends at Nextrong and Seagreen. HTC is the most carbon efficient and lowest greenhouse gas producing biomass conversion process. But HTC also increases efficiency of other biomass conversion processes such as AD and pyrolysis. And we have a levelized cost of transformation over 20 years about. That is about $20 to $30 per ton of wet waste. My time is up. For more information, check out these websites. And that's an excellent YouTube video on HTC done by Matt Farrell with his Undecided YouTube series. It's been really cool to have that as a resource, and I'm done.
Great.
Sorry,
Thanks,
Terry. I
Jeremy.
know I was pushing time pretty hard there.
Oh, that's okay. Thanks, Jeremy. Great presentation. I think we'll go ahead. We'll wait for questions at the end of Jim's the next presentation. Then we can have time for more Q&A.
Okay.
So move on to the third and final presentation today by Jim Euler at Genefuel Corporation, and he'll be talking about progress and status of hydrothermal processing for wastewater solids. Mr. Euler is the founder and president of Genofuel Corporation, formed in 2006. Genofuel provides hydrothermal processing systems which eliminate wet waste, especially wastewater solids, by converting them into renewable fuels. Genofuel has recently commissioned a pilot study scale hydrothermal processing facility and is currently in the engineering phase for several wastewater utilities in North America and Europe. Mr. Euler holds more than 20 patents issued or pending, as well as executive licenses to other patents for hydrothermal processing. Earlier, he held senior positions in energy consulting and corporate management, leading to 12 years as CEO of a publicly traded company. Jim, the floor is yours.
Okay, thank you, and good morning or good afternoon, everybody. So we'll be talking about hydrothermal processing, but we're switching gears a little bit here. Instead of oxidation or char formation, we're producing a hydrocarbon, either the simplest hydrocarbon, methane, or longer chain hydrocarbons, which are liquid oil, both fuels. So with that, let me give you first a general overview of this form of hydrothermal processing, or HTP. What we're doing here is we're using temperature, pressure, and water to convert wet waste materials, organic materials, into oil and gas. It's the same process that formed fossil fuels, where organic matter settled into swamps or shallow lakes, builds up over millions of years, produces temperature and pressure, and accomplishes the transformation. We're doing the same thing, but we do it in about 30 minutes instead of millions of years. The process conditions are higher than the char formation reactions that we've just been looking at. We operate actually just subcritical. We are not supercritical. Supercritical temperature is about 374 degrees C. We operate just below that. So we are subcritical, but up there at 350 degrees and 200 bars. The 200 bar pressure is not actually a reaction condition. It's a condition to keep the water liquid. We don't want to go to supercritical or vapor. We want to keep it liquid, although it's close to supercritical. And that set of conditions has been tested over many years to be optimal for this, for the hydrocarbon formation for hydrocarbon fuels. Most of this work has been done by the Department of Energy at the Pacific Northwest National Laboratory and optimizing the conditions for hydrocarbon formation. This will work with anything organic, really waste from almost any kind of stream, including wood and ag waste and chemical waste. It's been tested with over 100 different feedstocks, but right now we're focusing on wastewater solids because there's a real need in the wastewater industry for better methods of handling wastewater solids and resource recovery from that. So that's what we will talk about mostly, but I will from time to time talk about some of these other processes as well for food and animal waste. This is what the process produces. There's from the single input of a organic waste stream, we first, after heating up, we produce a collection or a precipitation of phosphorus in the feedstock. Wastewater has quite a lot of phosphorus, and it's precipitated as a solid, although it's still wet. So it's a wet solid, and that can be sent for fertilizer production. Chemically, it's identical to phosphate ore, and so it can be treated the same way to produce fertilizer. We get the oil, which is just like crude oil or petroleum, and it's processed the same way. So that oil, although you could burn it as it is, that's not what we would do. It would go to a refinery just like petroleum, and it would be refined into finished fuels. most biomass produces mainly diesel. It's typically most biomaterials will yield about 60% diesel. But the next most common product after refining is kerosene or jet fuel. So this is a hot topic in this era of synthetic aviation fuels, which everybody's looking for. Out of the oil stage, we get an effluent water. We still have water. The water is conserved. The water in is the water out. We don't use it. We don't add to it. But we do have some organic matter still in that effluent water. Not all of the organic content is converted to oil. In fact, about half of it is. The other half is still in that water. There's no solids. It's cooked down. It looks like brown tea, as you can see there. But that organic matter then is recovered in a second stage, which is gasification. The gasification stage is a catalytic stage, and it converts the remaining organic matter. The carbon is reduced to methane. And what's left is a clear, sterile water. It is sterile, so there's no BOD left at all. COD is typically about 50. So it's very low remaining content in the water. It's clear. And with a final process at the wastewater treatment plant, whatever the plant will be using for final process, that water can then be discharged. So I'm not going to go through this, but there are a series of stages. The first stage in orange is preparing the feedstock, and we process it as a slurry of about 20% solids. We can actually process anything from 10 to 30 or even 40% if you can pump it. And so it becomes a sludge handling issue, really. But we make a sludge which is as high in solids as possible, because that'll give the best yields. Then the hydrothermal liquefaction stage, which is the oil stage, the liquid stage. And then we separate the crude, pull it out, and the remaining, that brown tea, goes to gasification in the blue here. And finally, gas, separation of the gas from remaining water, so the water can be discharged and the gas can be, really what it's most commonly used for is to send it for insertion into a pipeline, right along with fossil methane. Just a background of how this came about. We first started working with wastewater sludge through a discussion with WRF in 2013. WRF was the Water Environment Research Foundation. That led to an elaborate and extended study called the LIFT study. There's a report on that. It's about over 200 pages. You can download it free of charge on what the successor to WRF, which was just WRF. That led in turn to a recommendation. The primary recommendation of that LIFT study was that this process works very well with wastewater sludge and should be implemented at a utility, integrated right into the utility. Metro Vancouver in Canada volunteered to be the utility for the integrated installation. So that started with detailed engineering, with the detailed engineering now in progress, and the plan for commissioning this system next year at Vancouver. It won't be the full size of a plant. The plant where it's being integrated is called Anaerobic Island. It's about 72 MGD. We'll just do a portion of that flow of about 3 MGD. But it will be fully integrated into the utility with all the pipes and pumps and controls to operate it right along with the rest of the utility. We've also done testing at Pacific Northwest Laboratory with multiple utilities to identify different types of sludge, different collection points within the utility, and so forth. And we're doing demonstrations now with a mobile system We've had it at several locations right now. This year it's been at Clean Water Services in Oregon near Portland, and it's currently installed at Altamont Springs in Florida, which is just north of Orlando. And we've also been processing sludge from Orlando's Iron Bridge plant. So just again, different types of sludge, different treatments. It's also been used to demonstrate algae and algae sludge mixes with AECOM. And we're doing later this year a zero emissions project at UCLA in California. So this mobile system has been kept busy. So current status. Currently, the largest system in operation has been processing since 2017, processing algae, but it's been hard for people to see because it's in India. But the important piece of this is that it's been running reliably since 2017. So it is known to be a usable and reliable process. And we will further expand on that with the Metro Vancouver system, which will be multiples bigger than this one. I'll show you that in a minute. We've also built this containerized system. It was first built to process dairy cow manure in California for the dairy industry. It was operational in 2019, but we've since upgraded it and used it on a much more focused basis for wastewater sludge. This is the 2023 startup for Metro Vancouver, and this is the Anaerobic Island plant there on the left. This happens to be a really great site because there's a refinery only 2 miles away from the Vancouver site. It's a little too far for a pipeline, but it's easy to transfer the oil by truck to this refinery. It's a small refinery. It's about 57,000 barrels a day. And its goal is to convert to completely green renewable feedstocks, starting with hydrothermal liquefaction oil from Metro Vancouver. This is what the Vancouver system will look like. You can't really see the dimensions on this, but the length of this, it's all skid construction in a factory, and then it'll be transported by truck and installed on the pad at Vancouver. The length of this picture, this ISO here, is 80 feet. The width is 18 feet and the height is 24 feet. So that gives you some feel for the dimensions. These things, like the others you've heard about today, have a relatively small footprint. They're compact. They process very efficiently, and they don't take up a lot of space. So here are some photos from the mobile system. This is installed when it was installed in Oregon. The two, there's a tank on the left here and another one on the right, which you can't quite see, but those are anaerobic digesters. So we were testing various stages, both primary sludge and post-digester biosolids. And we're actually going back here to Durham later this year because we didn't get as far with the biosolids as we wanted. And we're going to pick up again at that point. But we did move out in the middle of the winter because it got pretty cold. And this is a water system. And if it's not operating 24/7, you're in danger of freezing. So we went to Florida. We operate this and maintain it ourselves, but it can be done at a utility or by a third party. And there's various options for that. So now we're at Altamont Springs in Florida. This is a regional water reclamation facility. It's small overall. It's about 12 MGD, but it's a sophisticated plant that uses a Barden-Foe process and followed by aerobic digestion, no anaerobic digestion, and then dewatering of the sludge. This is what the system looks like inside on the left. And on the right, we show two feedstocks that we've processed here in Altamont Springs. One is algae, and that's a filter press on the upper right, and then a belt press on the lower right for dewatering the sludge from the plant. The algae got dewatered up to about 16%, and the sludge is at this belt press installation is about 12%. But we also got sludge from the Iron Bridge plant in Orlando, which is at about 18%. So we've been working with all of those and with mixes of the algae and the sludge. So now sludge processing, I'm going to walk you through this on the scale of this containerized system. A big system or a bigger system like the Vancouver system, or a full scale system like if it was processing the whole production of the Altamont Springs facility, would all be the same. We have the same processes in our container, just smaller. So I'll walk you through what we're doing with the container. It wouldn't be the same in a full scale plant, it would be different equipment, but at least you see the process steps that we discussed earlier. So it starts with the dewatering of the sludge. This is coming off of the aerobic digester, polymer addition, and then belt press to dewater. We collect it right off the belt press here and bring it to our system. So we bring it to our system, and our holding tank, if you will, is actually 55-gallon drums. We bring it over from the conveyor belt and the 30-gallon drums just because they're easier to handle. And we put it into 55-gallon drums. The 55-gallon drums, the sludge is stirred. So there's the stirring mechanism. And that stirring mechanism is lowered into the barrel after the sludge is added. And we found that to reliably feed higher solids sludge, we need to keep it mobilized. We need to keep it stirred. We also found that we need to heat it to reduce the viscosity a bit. So we have a steam sparger in the bottom of the tank. This tank is just showing that the steam is being injected, but you don't see that when it's actually running. So on the right, the stirring mechanism is being lowered into the drum. The steam will be started. We also have a cladding over the tank, which has hot water circulated in it to keep it warm, and a blanket. The next thing we do is we grind it with a grinder stage. This happens to be just a commercial strength garbage disposal unit, but we grind the sludge to make it smooth and easily pumpable. And then we pump it into our holding tank on the right here, which is also heated. And it's stirred as well. You see a pneumatic stirrer on the top. So we keep it moving, keep it stirred, and then we take it to the high pressure pump on the left. This is a small scale high pressure pump. It's capable of 5,000 PSI. We're only working at 3,000, which is 200 bar. But in a commercial operation like Vancouver, these would be much larger high pressure pumps, but industrial scale, industrial types. From there, it's pumped into a series of heat exchangers and vessels flowing down through the system here, basically just to provide residence time. That 30 minutes of residence time is what's needed to convert it. On the lower left there, that insulated device there is actually a heat recovery heat exchanger. It's a tube and tube heat exchanger, very efficient. So we recover the heat from the outbound products and bring it back to heat the feedstock. So this is the output, what the oil looks like coming out. It doesn't look much like oil here because it still has a lot of water in it, but that will then be separated. We're currently doing it by gravity, but in the commercial, the full scale implementation at Metro Vancouver, it'll be done by centrifuge to heat it up and get a higher efficiency of separation. We do have a centrifuge which we use here, but it's a batch centrifuge as opposed to continuous. Everything else in this process is continuous. So in conclusion, this process, we demonstrate here with the smaller system that this does work. We can make oil as well as methane gas. I didn't show the gas stage because there's not really much to see. It's flowing across the catalyst, and then the gas is available for insertion into a pipeline. This is an easily scalable system. We've scaled it already. I showed you that system in India. We're scaling with the system at Metro Vancouver. And in fact, the larger systems are actually a lot easier than this little system. And the reason is this little system has really small pipes. And so everything has to be, perfectly made into a perfect slurry and handled just right so you don't get plugging. But in the bigger systems where you get up to 3 or 4 or 6 inch pipes, that's not really an issue. And so it's actually much easier to build the larger systems. System design is emphasizing long-term reliability and operability. These systems are designed to be automated and run from the control center, the SCADA center of the utility. We would have some staffing on a prime shift, but not every shift. And it's intended to be reliable with a quarterly maintenance cycle and a once a year longer cycle of 2 weeks for making any equipment changes that are needed. Economic analysis shows that this is a positive impact on the utility. In other words, it's profitable. And it can be done either as a utility-owned system or as a build, own, operate, where a project developer would build and operate this system. That is actually pretty interesting to a lot of utilities because they aren't familiar with this yet, and they would maybe want somebody to do it essentially as a service in the early years. So that's a possibility. So there's contact information if you want to contact me later. And with that, I'm at the end, and thank you. And I think we have about 5 minutes left for questions.
Great, great. Thanks, Jim. Great presentation. So first question I see to you is what type of pump gets HTL to 3000 PSI? Well, that little one that we showed there is a syringe pump. I'll just go back and show you that. It's basically toggling. One side is filling while the other side is pumping. It's just a piston in a cylinder. And it's a screw that pushes the piston up in the cylinder and then retracts it to refill. But you wouldn't use that on the commercial ones. On the bigger ones, the one that we built for India, which has been working very, very well, is a ruggedized kind of membrane pump. It's derived from pumps that are used in mining to bring up gritty material from great depths. And we're also working with a new type of pump, which is experimental, but looks like it will have pretty good performance. It's almost like a peristaltic pump, but on a high pressure industrial scale. And we've also experimented with pumps like you use for concrete pumpers, where you're pumping very thick material up to great heights for buildings. Any of these will work, and it's a question of matching it to the flow requirements that you have for the particular installation. What type of pump's going to be used on the Vancouver? Or is
Vancouver, we're currently planning to use this peristaltic type. It's a combination peristaltic and membrane. It uses very thick tubes which are pressed to press the material and compress it. It sounds goofy, but it works in industrial applications. It was developed and used most intensively in Japan.
Okay. All right, great. Thanks, Jim. So I don't see any other specific questions to you. I know there were some previously to Jeremy. Jeremy, I see you typed responses to several of them on there, but maybe we could run through a couple of those questions for the group as well. And please feel free to type others. I think we got another couple minutes before we close out. So I did have a question for you, Jeremy. When in terms of the side stream, with that, they said, so I was going back to the headworks at the Phoenixville facility. Was the thought considered to use that as for anaerobic digestion? I imagine that's pretty high COD.
Yeah, it was. The Borough of Phoenixville wastewater treatment plant anaerobic digesters are at a point where they need to be revamped. So they're going to be moving away from their anaerobic digesters completely.
Okay.
Once HTC is fully permitted and ready to go, given the green light. But that's certainly an option for a wastewater treatment plant that has anaerobic digestion, or we could do kind of rapid digesters on site for biogas production.
Okay. I think I saw a question, some of the questions come up, but what, I guess for all the systems, what's the odor and the odor, potential odor impacts?
Yeah, I mean, and maybe y'all can say otherwise, but our products aren't as smelly as the feedstocks that we use. I know that working with sludge in my labs at Villanova, the professors would get very angry with me if I ever left the door open. The products itself are more coffee, earthy, burnt smelling than kind of H2S and the traditional odors from sewage. So I think odor control and negative pressure is going to have to be used for feedstocks. The products themselves are a different type of odor, and I wouldn't characterize them as malodorous. John, what do you think?
I'd agree, having spent a lot of time in the presence of paper mill sludge, for instance, especially as it ages. This has got it's got some smell from whence it came. So if you're familiar with sort of like a little bit of the sweet smell you get from wood that's been hydrolyzed, but you should be our spokesman for odors, Jeremy. I think you captured the issue well.
Yeah.
In our process, the hydrothermal liquefaction, it's almost odor free. You do want odor control though, because if there's any sulfur, the sulfur which gets to the catalytic stage will be reduced to H2S. So we have to capture that. It's relatively easy because it's captured ahead of the methane formation. The only other smell is the oil has a definite petroleum smell. Petroleum has its own odor. It doesn't smell like sludge. It doesn't smell like the feedstock. It smells like petroleum, but maybe a little stronger because there's a small amount of nitrogen in the oil, more than there is in petroleum, and nitrogen typically will give you an amplified odor. So the oil has a definite petroleum smell, but it's not a volatile kind of smell that goes off into the air very much. It would be handled more at the refinery.
Right. Well, great. Well, I think that covers all the time we have for today. I think the last question, thank everyone there, but I guess I know there was a question that came up about exhibiting at RBC, and it sounded like everyone may be there. Are all three of you having booths?
I don't have a booth, but I'll be presenting.
Okay.
I won't be there, but we will be at WEFTEC.
Okay.
This year.
We are figuring that one out.
All right. Well, great. Well, thank you all for the time and great presentations. I hope everybody enjoyed this. I know I certainly did.
Awesome. Thanks, Terry. Thanks, man. Appreciate it.
Thank you. Thanks a lot.